How are you all doing this morning?
Pretty good.
Doing well.
Good. How are you?
Doing great. So the first thing I would like to talk about today, before I kick it over to you guys, if you have any questions, is a mistake that I made in the video lecture. So let me go ahead and share my screen here, if I can. So a student pointed out correctly that when I was doing my power calculations for the 30 ohm resistor, I accidentally put in the voltage for Vx, and when I was doing my power calculations for the resistor over which Vx is defined, I accidentally put in the voltage drop over the 30 ohm resistor. So I made two mistakes that effectively canceled each other out, and so I just want to be clear about that. So the places, those voltages that are underlined in red, they should be switched. So yeah, sorry if that confused anybody. Just a simple mistake on my part. So any other questions regarding the video lecture then?
I'm good.
All right, nobody's saying much of anything. Largely, it's probably a review since you guys, since you all did learn about Kirchhoff's voltage law and Kirchhoff's current law and Ohm's law in your freshman classes. So if nobody has any questions regarding the video content, then we can go ahead and jump on over to working on the in-class assignment.
I had a question about the web work for homework 1.
Oh, sure, yeah, I can answer that.
Let me get to it really quick. I think it was problem. Yeah, problem 4.
Okay.
For part B, you're supposed to find the maximum charge in the time interval and the time at which it occurs. I was just making sure I did it correctly because I used the first derivative test from Calc 1.
Yeah, so sorry, I've got so many different computers in front of me right now that I'm getting myself a little bit mixed up. So let's pop in to Engineering 221, Homework 1,
Number 4.
Problem 4. All right, let me see if I can share this. If I can find my Zoom window. There we go. All right, so homework 1, problem 4. You were given the relationship for charge as a function of time, and your question was specifically about part B, correct?
Yeah, because it asked for the maximum charge first, but the way that I did it solved for the time first, and then I plugged that in to get the charge.
Oh, okay. So that's a non-issue, I would think.
Okay.
Yeah, how I would have approached this problem: take the derivative of Q of t with respect to time,
Yeah.
and then you're going to end up with a third-order polynomial function. One of your answers is going to be 0, and then you're going to have the square root of something. Let's see.
For me, it was 5. The numbers are going to be different.
Yeah. So I wonder if I can draw on this. No. All right. So let me write this down, and then we'll pop over to the engineering paper thing I have. So 17.7 t squared minus 3.5 t to the 4th. All right. Let's look at this guy. Okay, so Q of t was 17.7 t squared minus 3.5 t to the 4th power coulombs. So what you had suggested was that we take the derivative and set it equal to 0, which is perfectly reasonable. So dq by dt, where t is equal to 0, would be, let's see, 2 times 17.7 is going to be 35.4 t. 4 times 3.5 is going to be 14, so that's minus 14. That does not look like a 4. T cubed. And this guy is going to be equal, we're solving this for when t is equal to 0. So we can factor it some. There's a common factor of t. So that would be negative 14 t squared plus 35.4. So obviously one of our solutions, t is equal to 0, but that solution does not fit our interval of t is greater than 0 and less than 4 seconds. So our other solutions would be setting negative 14 t squared plus 35.4 equal to 0, which means t squared is 35.4 over 14. Plus or minus the square root of 2.528 for my numbers there. So only the positive root satisfies the condition that t ranges between, but not including 0 and 4 seconds. So yeah, it seems to me that finding the value of t is significantly easier than finding the value of q max. So find t and then plug that into the equation to get q.
All right, cool.
Any other questions regarding any of the homework problems or anything?
I have a little bit for number 5.
Number 5, all right. Let's see what's crack-a-lacking on number 5.
What's crack-a-lacking on number 5?
See, how do I get to the next problem? Homework sets. 1, 5. All right. So one thing that I'd like to point out here, it says, which of the DC sources above are absorbing power? What is meant by that question is which of the DC sources above are absorbing positive power?
Positive power. Okay.
Yeah, because they could all be considered to be absorbing power, but only some of them will be absorbing positive power. This is one of the things that frustrates me about the way some of these questions are worded is it's not obvious what is actually being asked for. So for this particular example, let's see. V1 has a positive voltage and the current I2 is flowing into the negative terminal. The current I2 is positive, so V1 is absorbing negative power because it's supplying positive power. So V1 is right out. Let's see, for the current source labeled I2, the current is positive. The voltage drop V2 is negative, and the current's flowing into the positive polarity terminal, so we have a negative absorbed power. So I2 is out based on the numbers that I have shown on the screen. For voltage source V3, the voltage is positive, and the current that is flowing into the negative polarity terminal is negative. So that means it is absorbing power because it is supplying negative power, means it's absorbing positive power. For the current labeled I4, let's see, I4 is flowing into the positive polarity terminal. The current is negative, the voltage is positive. So I4 is not absorbing positive power. let's see, V5, the current I6 flows into the positive polarity terminal. V5 is positive, I6 is negative, so it's absorbing negative power, so that one doesn't work. And lastly, we have the current I6 is flowing into the negative polarity terminal of the voltage V6. So I6 is negative, V6 is positive. It's supplying negative power, so it's absorbing positive power. So if my memory serves me correctly, V3 and I6 are the correct answers. So let's see what happens. I was right. What do you know? So it's very similar to what we did on the example that I did at the beginning of the last class, as well as in class assignment 1, problem 3, but you don't even actually have to do the math. You really just need to check the signs because that's going to tell you everything you need to know. Was that a sufficient explanation, or did I go through it too
So,
quick?
so if it comes out negative, the power, then that means it is absorbing power. Is that what you're saying? Okay.
So, okay, so we're checking using the passive sign convention. Okay, so what I did on each of those instances was I saw if the current went into the negative polarity terminal, then that means that it was supplying power. Okay, and if it's supplying negative power, that means it was absorbing positive power. So, for instance, on the current. The DC current source on the very right-hand side of the circuit, I6, okay? So that current is flowing into the negative polarity terminal of the voltage labeled V6. The current has a negative sign. The voltage has a positive sign. So that means that it is supplying negative power, which is the same as absorbing positive power. Did that clarify things at all?
Yes, sir.
Okay. Any other questions regarding web work assignment number 1? Has anybody started number 2 or anything yet?
I've got a question on number 1, problem 6,
Problem 6, all righty.
with the current I5.
All right, homework set number 1, problem 6. Sorry, you guys would have probably passed out seeing that ugly mesh problem. All right, and you're saying with the current I5, you said?
Yeah, or the power related to I5, I guess.
Okay, so the box to the left of I5, which has a voltage drop of V4 over it, is in parallel with current source I5, right?
Yes, sir.
They share the top node and they share the bottom node. So that means that the voltage drop over I5 is the same as that voltage labeled V4. So I5 has a value of 5 amps and it's flowing into the negative polarity terminal. So let's see, I5 times what I have as V4, so that's 5 amps times negative 8 volts, means that the current source I5 is supplying 40 watts for my numbers. You are asked to find the power absorbed by each element, so that means that it would be, if it's supplying negative 40 watts, it's absorbing positive 40 watts.
Okay, thank you.
Any other questions regarding the passive sign convention? It's going to be not necessarily difficult, but tedious, and it just requires an awful lot of practice to get comfortable with it. Like it's not uncommon for me to get questions about, hey, how does the absorbed versus supplied thing work, all the way up until the end of the class, to be entirely honest. So don't feel bad if you're not getting it right off the bat. It's a little awkward. All right, any other questions regarding the web work? Nobody saying anything. So let's pop on over. Stop. I'm trying to make these things go away without closing the Zoom meeting. All right. All right, looking through them previously. All right, so number one is just fairly straightforward Ohm's law. We're asked to find the voltage drop over the resistor and the conductance and the power absorbed by these elements. So one thing that I actually should have specified here, but I didn't, so that's my mistake, would have been a polarity for the voltages. So I'm going to go ahead and tell you the polarities that I'm assuming now. So we're going to try to find this voltage drop VR with this polarity and this voltage drop VG with this polarity. And that thickness is far too thick for my taste.
Would you be able to assume those polarities just given the direction of the 6 amp?
That is exactly why I assume those. So
Okay.
the expectation is that both of those elements will be absorbing power. So I want the current to be flowing into the positive polarity terminals. So that's why I chose those. So using Ohm's law, the voltage drop over the resistor VR should be fairly straightforward. V is equal to I, which is 6 amps times R, which is 5 ohms, is 30 volts, right? For our conductance, we know that I is equal to V times G. We're trying to find V, so V is equal to I divided by G. So VG is 6 amps divided by 1/4 of a Siemens. So 6 divided by 1/4 is the same as 6 times 4 is 24 volts with the polarities that we've chosen here. For our power, we could use now either, well, actually, we know both the voltages, so we can just multiply both of those voltages by 6 to get the power. So P, dang it, power absorbed by the resistor is just going to be 6 amps times 30 volts is 180 watts, and the power, that's not a P. Our conductance is going to be 6 amps times 24 volts. So let's see, that's 150 minus 6, 144 watts. We could have just as easily done I squared times R to get the power absorbed by the resistor, or V squared over R to get the power absorbed by the resistor. Similarly, we could have done V squared times G to get the power absorbed by the conductance, or I squared over G to get the power. Any of those expressions work. But since we already had the voltages and we knew the current, I just went with P is equal to I times V because I'm lazy. So any questions on problem 1 here? This one I felt was pretty straightforward.
You mentioned this in
Good.
a lecture. You could have also flipped or inverted the conductance value.
Right, so 1/4 of a Siemens is the same as 4 ohms. And I could have used that too. Yep, you're absolutely correct. Yeah, let's see, 6 amps times 4 ohms would have still given me 24 volts. And then 6 times 24 volts would still give me 144 watts. So yeah, I could have converted that conductance into a resistance and then gone that route as well. And everything would have still worked out perfectly. Any other questions or comments on this first problem?
I'm good.
Alrighty, let's move along to number 2. This one is a little bit more difficult. So we're asked to use Kirchhoff's voltage law to determine the unknown voltages Vx and Vy. And all we really need is Kirchhoff's voltage law by itself, nothing else. So what our goal here is to do is to, let's use that one, find a path that we can take that effectively isolates the variable Vx or the variable Vy, right? So Kirchhoff's voltage law is applicable for any closed path, meaning if we start at a point and we end at that point, it's good to go. So there are multiple different ways to do this, but I'm going to choose paths specifically that have only a single variable and known voltages. So if I start here, I can come down here and circle back. So that's one path that contains only the voltage Vx and known voltages. Does everybody see that?
Yes, sir.
Yeah. So I can write an equation starting at the bottom left-hand corner. I have negative Vx, because I see the negative polarity terminal of the voltage Vx first. Now I'm coming up along the top, and I see the positive polarity voltage of that 12 volt drop. So that's plus 12 volts. Now I'm coming around from right to left. I see the negative polarity terminal of the 6 volt source. So that's minus 6 volts is equal to 0. And I can rearrange this guy. So if I move Vx to the other side of the equal sign, I have Vx is equal to 12 volts minus 6 volts is equal to 6 volts. So one thing that troubles students, and I think I mentioned this in the video lecture, is this bit right here. So this voltage is simply the difference between this node, the potential difference between this top node and this middle point of the circuit. It doesn't have to carry current or anything like that. As long as there is a difference in electric potential, there's a voltage that we can deal with. So now let's find a path that we can get the voltage Vy. So I have a couple of resistors here, this guy and this guy, that don't have voltage drops associated with them. So I'm trying to avoid them, although I could technically figure out what those voltages were just using Kirchhoff's voltage law. But I'm trying to be, I'm trying to make my analysis as simple as possible, so if I can skip those, it'll be easier. So the path that I'm going to choose is this guy, because it avoids that unknown resistor voltage in the middle. So if I start from the bottom left-hand corner, as I did in the last one, I would have negative 6 volts minus 12 volts plus, sorry, forgot the V, plus Vy plus 4 volts is equal to 0. So Vy is going to equal to 12 volts plus 6 volts minus 4 volts is equal to, let's see, 12 plus 6 is 18, minus 4 is 14 volts. And so I was able to determine the unknown voltages simply using Kirchhoff's voltage law. So anybody got any questions about how I approached that particular problem? All right, nobody's saying anything, so let's jump forward to problem number 3. This is another one that tends to give students an issue. And so I'm going to have to do probably a little bit of explaining. So the first thing that I want to point out is that this is a single node pair circuit. So to be clear, we have this top node and this bottom node, and those are the only nodes in the whole circuit. I am going to be adopting the convention that currents that leave the top node are positive and currents that exit the top node, excuse me, currents that leave the top node are positive and currents that enter the top node are negative. So leaving is positive, entering is negative. Okay. So let's start with this current IX. It's going to flow through that 6 kilo ohm resistor. So it is entering the top node. So I'm going to have negative IX. The 6 milliamp current is entering the top node. So I'm going to have minus 6 milliamps. The current from the dependent source, 4IX, is exiting. So I'll have plus 4IX. This 2 kilo ohm resistor, some current is going to flow through it, but I haven't really specified anything yet. So I'm going to create a current with direction down. And I'm going to call it I2K. So since it's exiting, I'll count it as positive. Similarly, we have this 2 milliamps of current. It's flowing down, so it's exiting, so it'll be positive. And lastly, we have the current IY, which is going to flow down through the 3 kilo ohm resistor. So it is also exiting. So plus IY is equal to 0. So I have one equation and 3 unknowns. My unknowns being IX, IY, and this new current that I had to identify, I2K. So what I'm going to do is I'm going to use Ohm's law to get relationships that will put IX, IY, and I2K in terms of this voltage Vx. So let's start with IY. Could anybody tell me what my relationship for IY in terms of Vx should be? Oops, sorry.
Is it a Vx divided by 3 kilo ohms?
That's it. It's that simple. So current is voltage divided by resistance according to Ohm's law. So Vx over 3 kilo ohms. All right. Let's do I2K next. Somebody else tell me what that one's going to be.
Vx divided by 2k ohms?
Right, because it's the current flowing through the 2 kilo ohm resistor. So it'll be the voltage drop over the 2 kilo ohm resistor. Actually, maybe I should have explained that a little bit better. So because all of these elements are connected in parallel, that voltage Vx with positive polarity on top and negative polarity on the bottom is common to all of the elements in the circuit. So the 2 kilo ohm resistor also has a voltage drop over it, Vx, positive polarity on top, negative polarity on bottom. So we'll have voltage divided by the resistor value, 2 kilo ohms. All right. Now for Ix. Now notice that the current is flowing into the negative polarity terminal of the voltage Vx. So what that means is that to satisfy the passive sign convention, we would actually want the current flowing into the positive polarity terminal because we know that our resistor needs to absorb power, right? So negative Ix would be defined as Vx over 6 kiloohms. So Ix must be negative Vx divided by 6 kiloohms. Does everyone understand what I did there and why this extra negative sign has shown up here?
Yes, sir.
Will you explain it one more time?
Sure. So the current Ix, as we have defined it in the figure, is flowing into the negative polarity terminal. Okay. So far, all of the voltages that we have defined have been under the assumption that the current is flowing into the positive polarity terminal, which is why we're getting positive Vx divided by the resistor value. So whenever the current's flowing into the negative polarity terminal, we need to reverse the direction of the current, which would be negative Ix will be equal to the voltage drop over the resistor divided by the resistor value. So we have to add that extra negative sign because the current is flowing into the negative polarity terminal instead of the positive polarity terminal.
Okay, thank you.
Yep, that's a very, very common, I guess you'd call it a trick that's going to get pulled on you guys an awful lot in your homework assignments, especially these next few. So you really need to pay attention when you're writing your Ohm's law equations about whether or not the current's flowing into the negative polarity terminal or the positive polarity terminal. Because chances are, if you're not paying attention to that, you're going to get a wrong answer, even though the rest of your analysis is perfectly correct. It's just going to be a little frustrating to figure out what went wrong. So I'm giving you a heads up now. Be on the lookout for that.
Do you recommend that we probably draw out the circuits that way, or?
What do you mean by that?
Like draw it out, or like that way we can kind of see like whether it's negative or positive that way.
Well, yeah, so it's really up to you. Like I feel, you know, as we're following these currents Ix and Iy around, like it may be helpful. The way that I've drawn Ix and Iy is the current flowing through a short circuit, but it may be helpful for you to say, extend the line so that you can see, oh, it's flowing down through this resistor. Similarly, this one was flowing up through this resistor. So you could redraw the circuit to kind of better show what resistor the currents are flowing through and stuff like that. I think that could definitely be helpful. Okay, so at this point, we really only need to substitute things into our original equation. So one thing that I want to point out here is I'm going to make a couple of simplifications. So negative Ix plus 4Ix is going to look like 3Ix. So I'm going to have negative 3 and my, well, sorry, let's be clear here. So I'm going to have positive 3 because negative Ix plus 4Ix gives me positive 3Ix multiplied by negative Vx over 6 kiloohms. Plus I2K, so that's plus Vx over 2 kiloohms plus Iy is plus Vx over 3 kiloohms is going to be equal to my constant terms. So when I move my 6 milliamps over, it's going to be positive 6 minus 2 milliamps is 4 milliamps. And now I have one equation, one unknown, so this is going to be pretty straightforward to solve. So let's see, I'm going to use my calculator because I'm lazy, and the numerical solver. So negative 3 x over 6,000 plus x over 2,000 plus x over 3,000 is equal to 0.004. Solve for x.
Dr. Hartman,
Yes.
I was trying to catch you before you made the calculation. I just realized, is step 3 supposed to be a 4? The
Is
3 for the IX?
no.
Oh, no.
So the reason it's not is because I have positive 4 ix right here and minus 1 ix right there.
Oh, I didn't see that other one. Oh, you're right. Okay, I got you.
No problem whatsoever. So I combine those terms, and then I also combined this guy and moved them over.
Right.
Which is where that formula came from. Yeah, so I was making simplifications, algebraic simplifications as I went along. But maybe I should have been a little bit more clear about what I was doing. So if you solve this single equation for Vx, we get Vx is equal to 12 volts. And then we can plug Vx is equal to 12 volts into our equations for into our equations for Ix and Iy. And so Ix was negative Vx over 6 kiloohms, which would be negative 12 volts over 6 kiloohms is minus 2 milliamps. And similarly, Iy was Vx over 3 kiloohms. 12 volts over 3 kiloohms is 4 milliamps. There we go. So this last one was a little bit tricky, but I think it helps to reinforce how to properly apply Ohm's law. That was my intention anyway. So any questions regarding this problem? All right, nobody saying anything? Oh, sorry, go ahead.
I said no, sir. My bad.
Oh, no. So what I'm going to do real quick is I'm going to pull up the web work assignment again, and we're going to look at homework 2 real quick. I might give you guys some pointers if I can remember what's what for those problems. Let's see. So homework set problem 2, or homework set 2. Let's see, problem 1. Find the resistance if you know the current and voltage. That should be easy. Find power if you know voltage and resistance. That's easy. Find current if you know power and voltage. That seems pretty easy. Find conductance if you know voltage and power. Yeah, so all of those are just using the various formulations of Ohm's law and the power relationships that we developed during that section of the lecture. So that's nothing too wild and crazy. This problem tends to mess with people a little bit. So what I would suggest you do is you effectively untwist the circuit. So instead of having it in this weird twisted form, just draw it as a simple single loop circuit, one big rectangle. Now, one thing that we want to notice is as we follow this current Ix around, it's flowing into the negative polarity terminal of this voltage that we've defined as Vx. So your Ohm's law equation should then be putting this voltage drop in terms of, or putting Ix in terms of Vx. Ix is going to be negative Vx over 50 ohms. Yeah. You're going to have a lot of undefined voltages around your loop, and I would draw all of them with the current Ix flowing into the positive polarity terminal. And then this guy, just be careful that you recognize the currents flowing into the negative polarity terminal. So that's going to add a negative sign to your Ohm's law relationship. Let's see, this guy is a single loop circuit as well. So pick an arbitrary direction for the current. I would pick the current flowing counterclockwise, so it'll flow into the positive polarity terminal of this voltage Vx, and then assign all of your other resistor voltages in a similar way, and then use Ohm's law to put all of those resistor voltages in terms of your current I, and that should be pretty straightforward. And then let's see, this is a single node pair circuit. So notice the positive polarity voltage is on the bottom, negative polarity is on top. So Ix, Iy, and Iz, you could put all of those in terms of Vx, but notice that all of those currents are flowing again into the negative polarity terminal. So make sure to account for that in your expressions. And then problem 5. The voltage is 14.9 volts for some time interval and negative 14.9 volts for the succeeding same interval, and oscillates back and forth. The voltage drop is present across a 35 ohm resistor. Over any one period of the cycle, find the maximum value of the voltage. That's pretty easy. It's going to be 14.9 volts. The average value of the voltage. So if it's 14.9 volts half the time and negative 14.9 volts the other half of the time, the average value of the voltage should be 0. The average value of the resistor current should also be 0 for the same reason. The maximum value of the absorbed power, so when the voltage is at a maximum, it'll be V squared over R. And the average value of the absorbed power. So this is the part E here, is the thing that a lot of students get mixed up on. And it's going to seem awkward because if the average voltage drop over the resistor is 0, and the average amount of current flowing through the resistor is also 0, then it stands to reason that the average value of the absorbed power will be 0, but it's not. And the reason it's not is if we look at the voltage, or excuse me, if we look at the power absorbed by the resistor, when the voltage is on its positive half cycle, the power is going to be 14.9 volts squared divided by the resistor value. So for the first half cycle, based on the numbers that I have, 14.9 squared divided by 35. So for the positive half cycle of the voltage waveform, our resistor is absorbing 6.343 watts of power. Now for the negative half cycle, where the voltage is negative, our resistor is going to absorb negative 14.9 quantity squared divided by 35, also 6.343 watts of power. So even though the average value for the voltage and the average value for the current are 0, the average power will be V squared over R. And it's because when you take the power that way, it doesn't matter whether or not your voltage is positive or negative, the numerator is always going to be positive. Does that make sense at all?
Yes, sir.
All right.
Yes, sir.
So that's the stuff that you should watch out for on homework set 2. So unless anybody has any other questions, I'm going to work on uploading yesterday's in-class meeting thing to YouTube and Moodle, and then this one as well as soon as it finishes rendering and all that kind of stuff with Moodle.
I have a question about this problem. It's not how to solve it or anything. I'm just curious about how functionally you would have an oscillating voltage like that.
So that's a square wave,
Okay.
right? So let's draw a picture of what's going on. Let's see. That's the one, right? So let's draw a graph. attempt to draw a graph. My fat fingers will get out of the way. So here's t is equal to 0, and then here's going to be where it first switches over, and then again, and so forth, right? So it starts off high, and then after some duration of time, it drops low, and then goes high again, et cetera, et cetera, et cetera. So this is literally, I guess it's not really a square wave so much as it's a rectangular wave. It's just a series of identical pulses. So if you have a DC motor, DC motors have a device all in them called a commutator. And what the commutator does is effectively switches the polarity of the DC voltage that's applied to the motor every half of a cycle. In order to maintain the rotation that's required. Because if you didn't, it would settle at a point where the magnetic flux through the windings of the motor is constant. So just effectively, every so many seconds, it flips the polarity of the voltage. And then every another X number of seconds, it flips the polarity back over and over again.
That's pretty cool. I've seen I don't know if it's related, but I assume it is, stuff on oscilloscopes like that.
Yeah,
Where
so
I see rectangular waves.
yep. So your analog wave generators typically can generate sinusoidal waves, rectangular waves like this, and also triangular waves. And when we deal with op-amp circuits, we're going to talk about how they can be used to integrate and differentiate signals. So like if you can produce a square wave, if you integrate that, you get a triangular wave. Or similarly, if you can produce a triangular wave and you differentiate that, you get a square wave.
Oh, okay. That's really cool.
Yeah, so it's just one, it's a couple of components. If you can generate one and then feed that signal through a small network, you can generate the others pretty easily.
Okay.
Actually, fairly common-ish electrical engineering senior design project for students to develop their own analog wave generators. So they just take a raw signal and then do lots of processing to it to make it look like sine waves, square waves, and triangle waves and all that kind of good stuff.
Cool.
Any other questions?
You
No,
said
sir.
you were designing something for where you work. What do you do?
So in addition to being the program chair for the electrical engineering department here, I also work for Sabre Industries out of Bossier City, Louisiana. And I work on designing the DC bus systems for battery energy storage containers. So are any of you guys familiar with like Tesla's product, the Powerwall?
No, I haven't heard of it.
Okay, so the Powerwall is effectively just a big battery that's used to provide supplemental power to a residence or small commercial application. So for instance, have any of you guys ever watched anything like Building Off the Grid? Okay, I guess not. Well, you got to watch more dorky TV shows. So when you have a solar system, if you don't give some form of energy, if you don't attach some form of energy storage to that, like whenever the sun goes down, you don't have power for the rest of your home, right? So it's typically done by using simple battery systems. Well, the company that I work for develops battery systems for large-scale industrial projects. So one of our most recent battery energy storage projects was for the Los Angeles Water and Power District, where they have a huge solar plant out in the Mojave Desert, and we provided their energy storage means for that.
That's really cool.
Yep. And so we got projects. We have one small building helping to reduce the power footprint of the San Diego Zoo. We have several buildings all over Japan, the islands of Guadeloupe and Martinique. We got a whole lot of projects in Canada, and we're getting more and more actually here in the States as people are starting to pay attention to trying to not rely so much on fossil fuels for energy generation. Probably a lot of people don't realize that a lot of the electricity that is provided by the grid is generated by burning coal. So we're trying to utilize greener energy techniques and lower your electric bills at the same time by making large battery storage projects that can supplement the grid.
Cool. Thanks for telling me.
Yep, no problem.
Dr. Hartman, I have a question that's kind of off topic.
Sure, go for it.
For the in-class assignments, like the submission on Moodle, do you care what we name those assignments? Like, do you have a specific way you want us to fill out that submission?
Not particularly. The only restriction I have on it, which I think somebody emailed me about it, and I kind of told them what was what. I want it to be one file just because it's annoying for me to have to create folders and put all the files and then do the combination myself. So it should be a PDF file. I'm not really particularly concerned with how you name it or anything, because I'm really just looking to see whether or not you uploaded it. We're working the problems in class, and by we, it seems to be mostly me at this point, but that's okay. And they have always been graded on a not even complete, so not for completeness and not for correctness, but just, are you participating? It's really just an attendance grade. So there's no point me being a stickler about how things are uploaded. I'm literally going to look to see that you uploaded a file, and if you did, you get credit, and if you didn't, you don't get credit.
Okay, thanks.
Any other questions? All right, nobody's saying much anything, so I will get back to editing videos and all that jazz and catch you guys on Thursday, because today's totally Tuesday, I think. Yeah. All right, have a good day.
You too.